Okay, so what I want to do for the last class is just choose what in my mind is a fun problem. I'll choose a lower chair. That allows us yet again to review a lot of the tools and techniques we've been using all semester, see a little bit where they go, and see some things in mathematics that you probably have not seen yet. If there's time, if people want to, I'm happy to play the M&M game. I have brought M&Ms and some pennies. Okay, so this is a version of a talk that I gave a couple of years ago to the 110th anniversary meeting or something like that to the Math Teachers Society of Massachusetts. And so when I was giving the talk to them, what I wanted to emphasize is that the world is changing. There's a great series of videos, Did You Know, about just how fast the world is changing, that a lot of what we're training you to do in college, by the time you get out into the real world, is already going to be obsolete. And so I showed you the punch cards from yesterday where they were talking about, 1982, the computer punch cards are now up to 960 items per punch card. A lot of this technology is not used anymore. What are you learning in college right now that will be useful later in life? Being brutally honest, most of the facts you learn are not going to be that useful. But learning how to learn, learning what's out there, learning what things can be solved, what methods you can use, that's the more important thing. And so what I want to talk today about is how to attack a new problem, how to see connections between different things. As you know, one of my favorite quotes is, if all you have is a hammer, pretty soon every problem looks like a nail. We want to convert something new to something we've seen before so we can comfortably attack it. All right, so a couple of general advice. Ask questions, not just in talks, not just in classes, but in life. Why is something going on? Why are we looking at this? A lot of times people are looking at the wrong things. They just get so focused on what everybody else is doing that it's very hard to think outside the box. Gather data, observe, simulate. There's a lot of problems that are extremely difficult to attack analytically, but we can write code and get some feeling for the answer. And frequently, if you do a couple of small cases, you'll start to see patterns. And those patterns will suggest what the answer will be. And I'll actually show you a website towards the end of today's talk that will allow you to get formulas or conjectured formulas for the patterns you're seeing. Now, of course, as a teacher, what do you want to do in a classroom setting? How do you engage people? Well, I'm in a department that is extremely committed to making their classes engaging. You will not always have that opportunity. You will have to give some technical talks later in your life, potentially. You want people, however, to be excited and interested in paying attention to what you're doing. Think about how you present. For what I'm doing today, I'm going to present it through a game. A lot of you will be presenting material to people who know less math than you, but they're the ones who can say yes or no. And you're going to have to convince them. You will have to find ways to make them listen to you. We're the only department on campus to still require people to give a colloquium talk to graduate. Unless you're going to be a mime, you need to be able to speak to people and communicate. All right, so the last is I want to talk a little bit about implementation. So this is joint work with Cam and Kayla. We've actually now written a paper on this with some of my students from last year. So hopefully in a few months, Cam and Kayla will have an Erdős number. All right, so I want to describe the M&M game. So when Cam was 4 years old, he asked me the following question. If you're born on the same day as someone, do you die on the same day? So how do you explain randomness to a 4-year-old? Well, one possibility is my wife is an identical twin. So I just go to a family meeting with my wife, her twin sister, and a machine gun. Well, there are a lot. I see some looks of shock in the audience. So there are some issues. While mathematically, this would be a great way to convince Cam that if you're born on the same day, you don't die on the same day. There would be many, many, many issues with that proof. So we want another way of convincing Cam and his 2-year-old sister, Kayla, that if you're born on the same day, you do not necessarily die on the same day as someone else. So we created the M&M game. This is what they looked like back then. Anybody notice anything about the M&Ms? So this is Kayla's column, Cam's column, and my column. Yes, when you're 2 and 4, it actually matters which colors you have. Now we talked about Galileo when he was dropping the spheres from the Leaning Tower of Pisa. The color probably doesn't matter. When you're playing with little kids, the color matters. And Kayla really wanted the blue M&Ms. So the way it worked is we all started off with 5 M&Ms, but more generally you could do K M&Ms. And we all tossed a fair coin at the same time. And if you got a head, you ate an M&M. And if you got a tail, you didn't. And then we would toss again and again and again. And we would see how long did you live. And when you ran out of M&Ms, you were dead. And then we would just do this and see how often do we all die at the same time. Turns out one of my kids' friends, their grandmother writes children's stories. And she wanted to use something like this, but didn't like the fixation on death and wanted a happier version, which is just sadly not true, so negotiations broke down. Yeah, it's about dying. That's where the question came from, trying to explain how death, okay. Looking at lots of shocks. All right. So what kind of questions can you ask? You know, that's one of the first things of today. What kind of questions could you ask about this game?
Average lifespan.
Average lifespan. How long until you die? And that should be some nice function of k, hopefully. What else could you ask? The variance. Right? If you meet a distribution, ask its mean, ask its variance, then see if it wants to have dinner. Okay. What else could you ask? Given that the original question is if you're born on the same day, do you die on the same day?
What's the average difference between when you die?
What's the average difference between you die? How often you die on the same day? So natural questions, we basically got all these. You could generalize the game. You could have more people. You could have a biased coin. Let's gather some data. So here, you know, if there was more time, I would actually have us flip the coins. But I know there's ice cream at Peresky today, and I know people might want to go to that.
Ice cream?
I'm pretty sure there's ice cream at Peresky from 11 to 1.
What kind of ice cream? Like, ice cream?
I don't know. All I know is that there is ice cream. So here are some just brute force calculations. And you know, here's the probability of a tie. So with one M&M, 2 people playing, 33% chance of a tie, 19% roughly with 2 people, et cetera, et cetera. In the past, you know, there's enough people in this class that if I were to do the experiment, it would actually go out pretty well. What do you think happens if we go out to, say, 110 people? Anybody want to hazard a guess for what the probability will be? I want to extrapolate this table. 0.2. How did you get 0.2? 0.0, so it goes all the way down to 0. It's kind of tough to see how rapidly it's decaying. 0.2 seems a bit high. 0.02 seems a lot better. I don't really expect the probability is going to start skyrocketing upwards. Let's go up to about 110, and so here is 0.1, 0.2. So 0.2 seems pretty reasonable. So I gave this at the 110th anniversary. That's why I chose 110. What do you think it would be if we went up to 220?
0.01.
Maybe 0.01. I want the next digit.
0.005.
0.005. Does everyone agree that it's kind of tough to just look at this and see the trend? What could we do to make it easier? Take a logarithm, right? When in doubt, in my class, either say take a logarithm or take stats to a 1 or take linear. You know, these are the basic answers, okay? And if we take a logarithm, it's going to be much better. All right, so welcome to statistics and inference. All right, this is a co-listed class. Let's use a little bit of this stuff. So it matters how we show the data and which data we show. So again, it's very hard to predict what comes next. But if we take logarithms, if we do a log-log plot, this is much easier to understand. What does this look like? This looks like a line. We know how to extrapolate straight lines very easily. You know, we would just continue the pattern. We've talked about the method of least squares. We can find the best fit line through the data. And we get the log of the probability of a tie is negative 1.4 minus 0.54 times the log of the number of M&Ms, or the probability of a tie when you start with k M&Ms is about 0.2412 divided by k to the 0.54. And so it predicts the probability of a tie when k is 220 is about 0.01274. The answer is 0.0137. So first of all, good job or bad job? I'd say it's not bad. You know, it's ballpark. But we are off by a sizable amount. We've got the first digit right. Second digit, we're missing a significant amount. So we're missing about 0.1 out of about 0.14. or maybe so it's a sizable error. The problem is these are very small numbers. If this was 50.0124 versus 50.0137, great, we're doing a wonderful job. But if you look at the relative error is large. Why do you think we've done such a bad job?
The least squares is magnifying some of the errors in the lower.
Yeah, so remember, least squares, if you have an error, the least squares the error. So a couple of really large errors have an enormous sway. So these few points over here in the beginning are really pulling the least squares line, the best fit line. Do we have any reason to suspect that these points may not be as good as these later points? Why?
Because since n is small, the number of evidence is small, then the behavior that you expect to find when n is large.
Excellent. The limiting behavior hasn't set in yet. So when we have small values of n, the limit hasn't been reached. And those small discreteness, going from 1 to 2, 2 to 3 makes a huge difference. Going from 200 to 201 M&Ms, not a huge difference. So whenever you have data, it can be very easy to be misled by small data in the beginning. And you're not going to see the correct behavior. What should we do? Cut those out. So let's just go from 50 to 110. All right. We talked about equidistribution and the fractional parts of n times the square root of pi, I think on Wednesday. And I stopped at one point and I said, if you have really good vision, you can see that there's small fluctuations at the top. Who's able to see the red line? There is a red line. The easiest place to see the red line is at the very, very beginning over here. Why is it so hard to see the red line? It is a great fit. The limiting behavior has really set in by 50. And so now we get a prediction of 0.01344 for k equals 220 versus 0.01347. That's extremely accurate. And so this is a nice example of the method of least squares in practice. What can we use it for? It's also a good warning about how you can misuse it. If you use it too soon, if you use it on too much data, those small values in the beginning can pollute the limiting behavior. Okay, so the next part is something we can go over very quickly. We've seen this numerous times. We started the semester with it. We will end the semester with it. All right, does everybody still remember who these two players are? Excellent. Okay, Larry Bird, Magic Johnson, coming back. So Bird and Magic are alternating shooting baskets. First one to get a basket wins. Bird always gets with probability P. Magic always gets with probability Q. We want to find the probability Bird wins. Well, we saw that we could break this into cases. This is our introduction to partitions. And the probability of an event is the sum of the probabilities of all the disjoint ways it could happen. So he could win on his first shot with probability P. To win on his second shot, they both miss. The third shot, they both miss twice. And then et cetera, et cetera, et cetera. The nth shot, they each miss n minus 1 times, and then Bird gets it. We get a nice geometric series, and we get x is equal to p times the geometric series, where we're letting r be 1 minus p times 1 minus q. We showed we could solve this without knowing the geometric series by using a memoryless process, by saying if we want to calculate the probability Bird wins, it's p plus, now they both miss, and once they've both missed, since Bird has the basketball now, it's like we've just started the game again. And so the probability that Bird wins from this point is just x. This is one of the key ideas of the whole semester, is if you can get something memoryless like this, you can convert something that's infinite to something that's finite. In general, infinites are very hard to work with. If you can convert anything that's infinite to finite, you have made enormous progress. You can now do it on a computer. So now we get x equals p plus rx. We solve, we get x equals p over 1 minus r, and that even gives us the geometric series formula. All right, so what did we learn from this? So we learned the power of perspective. We learned memoryless processes, that there's good ways to circumvent algebra. As you go further and further in mathematics, algebra becomes more and more important because the expressions are so involved. You want to find good ways around it. One of my more successful papers was I actually found a really nice simplification for a ratio, and I saw that I could actually write this in terms of another ratio, which was well understood. you need to be able to figure out how to see things, especially if you want to try to get a sense of how does my answer depend on my parameters. One of the reasons economics is so difficult is the behavior is so complicated. We don't have closed form expressions. We have to resort to simulations. Simulations are expensive. If you have a parameter that you can just vary and see how I see some people smiling. Are you stuck doing econ simulations? Yes. And so you know how long it takes to run things. If you have a nice closed form expression, wouldn't it be wonderful if you could just plug this in and see if the Federal Reserve changes the interest rate to this number, what that does to the US economy? It would be wonderful if we had something like that. We don't. Another thing is the depth of a problem is not always what you expect. Sometimes a problem that looks hard is actually easy. This is not an infinite series to sum, it's actually a finite sum. The other thing is there's an extreme value to knowing a lot of mathematics. The more math you know, the more connections you can see. I'm not expecting you to remember most of what you've learned in college, but I want you to at least remember that you learned it at one point, so that when you see something later in life, you go, hey, this reminds me of blah. I remember being bored, but I remember we did something about this in one of my classes. And then go back to your books, go to what website? To look something up, what would you go to? Yeah, Wikipedia or Google it. Quickly do some search. If you know which words to search for, if you know what concept to look up, you will find terrific resources on the web. But you need to know what's out there. All right, so let's look at the MandMGame a little bit more carefully. The first approach is to overpower it with algebra. Here is the answer. It's the following infinite sum. This is the probability when we have k M&Ms and two people that we end in a tie. Why? Well, if we end in a tie, then we could end in a tie after k tosses, k plus 1, k plus 2, k plus 3. Could we end in a tie in fewer than k tosses? No, you have k M&Ms. Kayla still talks, she remembers this from when she was 2, about the day we played and she got 5 straight heads and died as quick as possible, but had no delay in eating her M&Ms. It made that much of an impression. If she was here, she would talk about that day with a smile on her face about how quickly she got to eat the M&Ms. But you can't go faster than that. You can't eat in fewer than 5 tosses. So if they end up as a tie, let's say they end up in a tie after n tosses. What must be true on the nth tosses? If they end as a tie, what must be true on the nth toss?
Same number of heads.
Not just the same number of heads. What happens on the nth toss? They both get heads. Those are the 1/2s. In the previous n-1 tosses, Cam has to get k-1 heads, and Kayla has to get k-1 heads. There are n-1 tosses. I choose k-1 of the n-1 to be heads, and then of course the remaining ones will be tails. Each one, because it's a fair coin, has probability 1/2. That's the 1/2 to the n-1. So this is the probability that Cam dies on his nth toss. This is the probability Kayla dies on her nth toss. We just multiply them together. Do those distributions look familiar, those probabilities? We've seen this distribution once or twice. Yes? Negative binomial. You're waiting for your kth success. So all we have to do is evaluate this infinite sum. We evaluated the basketball one. We could do it by the geometric series. How many of you want to try to evaluate this infinite sum involving products of binomial coefficients? What would you love to do? What's our goal? Make it finite. Anybody have any thoughts as to how we could make this finite? How do we make the basketball finite? What did we notice? Memoryless. How do we get memoryless? What happened to give us a memoryless? We went back to the beginning. Now here it's a little bit more complicated because we have multiple M&Ms. But what do you think is going to be the equivalent of the reset we got in basketball? So Kim and Kayla tossed their coins. What outcome do you think is going to be equivalent? If they both get tails. If even one of them gets ahead, the total number of M&Ms not eaten in the universe has decreased. As long as one of them gets ahead, the total number of M&Ms is falling. And it'll keep falling until it gets to 0. The danger is if they both get tails. But if they both get tails, what do we say? Start over. Pretend that toss didn't happen. Okay. Before going into that details, just so it's in your radar screen, this actually simplifies. There is a closed form expression for this infinite sum. It's 4 to the negative k times the hypergeometric function evaluated at kk 1 1/4. So you should at least be aware that hypergeometric functions exist. You are now aware that hypergeometric functions exist. I can check that off my to-do list. All right. They are wonderful, but just because I write something down in a closed form like this does not mean it's useful, unless I have a nice way of getting information out of this hypergeometric. But maybe I can now somehow get some nice k-dependence from this, because a lot is known about these very special functions. They solve nice differential equations. A lot of the classic functions are actually special cases of hypergeometric functions. And I'll put some reading for people who want to know more. All right, so we talked a little bit about where this formula came from. There are 4 equally likely events. They both eat, only Cam, only Kayla, and neither. The probability of each eating is 1/4 or 25%. And that's what led to our wonderful formula. Okay? And now we're going to rephrase it. We use, as we said, the hoops game. We use the memoryless. There are only 3 possibilities, because if now they both get a tail, we can just pretend that didn't happen, and it makes the game finite. How many moves will it take now, worst case scenario, for the game to end? Approximately. They both start off with k, and now we've eliminated the double tail. How many moves will it take, worst case scenario? 2k. You can do a little bit better than 2k, because the last one has to be they both get heads. So it's probably k minus 1 plus k minus 1 plus 1. So it's probably 2k minus 1 is the worst possible case now. But 2k is a fine estimate. So we've now converted it to a finite sum. And so now what we want to do is we want to calculate what's the probability that it takes n tosses. And now we can go through. And so here is the wonderful expression. And we have to keep track of how many times does Cameron get an M&M eaten but not Kayla, how many times does Kayla get one but not Cameron, how many times do they both get one. So what we're going to split on is on how many times they both get ahead, or equivalently how many times just one of them gets ahead. Because if Cam gets ahead exactly 4 times by himself, then Kayla must get ahead exactly 4 times by herself if we're going to end in a tie. So that's where the sum is coming from. I'll let you ponder exactly where this is coming from. What's nice is all the probabilities are 1/3, so everything is going to be very nice. And we just need to keep track. If they both get ahead, we're going to lose 2 heads, 2 M&Ms from that. If only one of them gets ahead, we only lose 1 M&M. All right, so this is now a finite sum. If I give you the value of k, can you compute this? Especially if k is a number like 1, 2, 3, or 4. For small values of k, this is no problem. What about large values of k? Maybe it's worth learning what the hell a hypergeometric function is, because there's a nice closed form expression for that. This formula is looking a little bit intimidating as k gets large. We have binomial coefficients where we have k-dependence both upstairs and downstairs. All right, so here's an interpretation of what's going on. So we'll assume Cam has C M&Ms and Kayla has K M&Ms. Why am I using those as my labels? That's their names. Why do I want to use their names as labels? I'm sorry? It's good notation. Spend time thinking about notation. You're going to get very complicated formulas. If you can glance down and say, oh, that's the M&Ms Cam has, that's the M&Ms Kayla has, it's going to allow you to understand what's going on a lot better. So really think about what you want to use for your notation. So basically, on a given turn, these 3 things can happen. We can go from CK to C minus 1, K minus 1, to C minus 1K, or to C, K minus 1. So here's a flowchart. Here is another way to attack the problem. We start off, I know in the original version of the game it's supposed to be 5 M&Ms. It was painful enough to get this to fit where you can still see the subscripts with 4 M&Ms, so I'm going to stop here. All right, so we'll do 4 M&Ms. And at each stage, there are 3 ways you can move. I can have Kayla eats, both eat, or just Cam eats. Each of these arrows has probability 1/3. What do you notice about all the vertices? Or maybe almost all the vertices? Do you notice anything? What patterns do you see?
You can always get to the blue dot unless one of them has run out of M&Ms.
Yeah, the blue dot, the 0, 0, you can always get to unless you've run out of M&Ms. There's always going to be a way, which makes sense. You know, the game is never over as long as you still have one M&M. This is very different than games like football where you can run out at the clock. It's like more like baseball, where as long as the game is not over, you can score as many runs as you need. What else do we see just by looking at this? Look at everything other than the first row and the last row. What else do you notice? Something about every vertex. Every vertex has an interesting property. What do the arrows represent? So somebody tell me what the arrow represents. An M&M being eaten. So an arrow going in this direction represents Cam eats, an arrow in this direction Kayla eats, and an arrow going down, they both eat. Do you notice anything about number of arrows? Yes?
3 arrows.
There's always 3 arrows coming out of every vertex except for the bottom row. And the reason is as long as both have M&Ms, both options are available. So all 3 options are available. If you're going to end up in a tie, where must you be one move before? You have to be at 1-1. Because you have to be going straight down if you're getting a tie. So really, we just have to calculate what's the probability we get to 1-1. Because once we get to 1-1, what's the probability we have a tie from 1-1? It's just 1/3. So what we can do is we can assign probabilities, and we can look at the flow of probability from here. What's the probability we start off at 4-4? 1. And we'll see how the probability flows. So after one step, we get 1/3 of the time will be at 4-3, 1/3 of the time will be at 3-3, and 1/3 of the time will be at 3-4. Now we flow again. We can flow from here, we can flow to 3-3, we can flow to 3-3 from here, we can also flow down. So what I'm going to do is I'm going to first have the probability flow out of 4-3 and 3-4 to here. And then, once I have all my probability here, I'll have that flow out. It's not a long calculation, and you'll get the calculation for the next row. And then we just keep going. And we can say now here we can have probability flowing here or down. And then once here, these can flow down or to here. And so we just keep going, and we keep going, we keep going, we keep going, we keep going. And eventually we get 245 over 729. And then we have to multiply by 3 in the denominator by 1/3, and we get 245 over 2187, or about 11%. Okay, so let me show you some connections to the Fibonacci numbers. So we've seen this many times. We've seen Binet's formula from generating functions, this beautiful closed form expression for the Fibonacci's. By now you know I love closed form expressions, especially for the Fibonacci numbers. It allows you to bypass a lot of calculations and have an answer you can just work with. Now, the Fibonacci's came from a really nice recurrence. Fn plus 2 is Fn plus 1 plus Fn. Here is our recurrence, xck. So xck is going to be the probability we end up in a tie given that Cam has C and Kayla has K. It's going to be 1/3 xc minus 1 k minus 1 plus 1/3 xc minus 1 k plus 1/3 of xc k minus 1. This is essentially going to reproduce the tree we just saw, but allow us to do it more formally and more algebraically. What's the big difference between this and the Fibonacci recurrence? There's a major complication here, yes? There's 2 indices. 2 indices are a lot harder to deal with than 1 index. And that's going to cause enormous difficulty. Now, some of the initial conditions are very easy. As long as Cam or Kayla has an M&M and the other has no M&Ms, what's the probability that the person with M&Ms wins? 100%. What's the probability of a tie? 0. So we know the initial conditions. We know xc0 equals x0k equals 0. If they both start off with no M&Ms, what's the probability of a tie? It seems reasonable to define that to be 1. And this is very similar to what we had with 0 factorials. How do you want to define things? You want to define things to make things nice. Well, our whole goal is to flow down and get to the x0, 0. So let's just say if they both start off with 0 M&Ms, it's a tie. Nobody wins. Nobody died before the other. So it's very reasonable. You really want to spend time and think about how you want to define things. You really want to spend time thinking about extreme cases. Now, why were we able to get this simple recurrence? What was the key observation that simplified things? How did we get to this? We had a really good observation. There are 3 ways. So what did we eliminate? What if we didn't see that? What if, I haven't, hammered home yet enough how important memoryless processes are. Maybe you were asleep for those 12 lectures and you did not think to, try to prune the algebra. I claim we would get the following recurrence. There would now be 4 cases, all 4 equally likely. What would you do with something like this? How would you tackle this algebra? You bring it over. So one of the very first integrals we did on homework was the bring it over method, where you had your expression on both sides of the equation, and then you bring it over to the other side. That's essentially what's going on in the memoryless process. You have your quantity on both sides, you bring it over, and now you can solve for it. And that allows you to convert the infinite to a finite. We bring it over. And when we bring it over, well, we get 1 minus 1/4 is 3/4 equals 1/4, 1/4, 1/4, multiplied by 4/3, and there's your recurrence. So if you didn't happen to see the simple recurrence, now after the fact, maybe you can go back and say, oh, wait a minute, oh, it's simplified. Why is it simplifying like this? I can just remove the tail case. And so this is a nice way to get to that key recurrence. And so now we want to solve this recurrence. I do not want to go into the theory of 2 index recurrence relations on the last day of class. This is not a good choice. Let's just go through it by brute force. If the values of c and k are small, brute force is fine. The other thing is, what would love to solve a recurrence like this? What would be really good at solving a recurrence like this? Computer, right? And what you do is you would just build out. So we start with x0, 0. What's the next one we would try to get? We know 0, 1, and 1, 0 already. Those are going to be 0. So what's the next one we try to get? 1, 1. And so we know x1, 0 is x0, 1 is 0, so we get x1, 1, we use our recurrence. Notice that when you use the recurrence, every pair here, the sum is smaller than the pair here. So you reduce it to an earlier case. So now we can get 1, 1 in terms of things whose sum is at most 1. And here 1, 1, the sum of that pair is 2. Well, we know those values. We plug it in, we get 33.3% approximately. What's the next one we try to get now? Two, 1, and 1, 2. So we know x2, 0 is x0, 2 is 0. Now to get x2, 1, that's the same as x1, 2. We use our recurrence, and this now reduces it to 3 things where the sum of the pair is smaller than 2, 1. Well, by previous work, we know everything where the sum of the pair is at most 2. So now we get x2, 1 is x1, 2 is 1/9. And now we can get x2, 2 by using the same thing again. And we can just keep iterating like this. It's not that bad. What can you tell me about all the answers? What kind of numbers will these be? Yeah. They're all going to be rational numbers. So it's always going to be a rational solution for this probability. Okay. So the other thing is, trying to find simple cases and building some intuition. So I want to show you some other ways. We're walking from 0, 0 to kk with allowable steps of 1, 0, 0, 1, and 1, 1. And we want to hit kk before we hit the top or the right sides. So how many of you have seen the Catalan problem? I know some of you might have seen this in discrete mathematics. Has anybody seen Catalan numbers? All right, so if nobody has done Catalan numbers, I'm not going to really go into too much detail. I'll just say here's a standard problem in combinatorics. You start at the lower left, you want to get to the upper right, you can only move east and north. I think we might have had something like this on one of the exams, where we were trying to avoid evil Amherst students, and there was a nice binomial answer. So if you want to count the number of ways you can do this, where you don't cross the main diagonal, this is the Catalan numbers. These turn out to be extremely important in combinatorics. When we did random matrix theory, we did the semicircle. Anybody want to guess which sequence of numbers are the moments for the semicircle? The Catalan numbers. The Catalan numbers turn out to be the moments of the semicircle. It's amazing how everything is connected. There's huge combinatorial significance to this. There's lots of beautiful ways to get these with generating functions and to count how many ways can you go where you never cross the top. Beautiful, beautiful recurrence relations. We're doing a generalization of the Catalan numbers. In the Catalan, you can only move east and north. We have 3 directions. All right, so I'm going to skip the rest of that analysis. What I want to do now is I want to talk a little bit about examining the probability of a tie. So we have beautiful finite formulas. I calculated the probabilities for k goes from 1 to 8. Here are the probabilities of the tie. What do you notice? Do you notice anything? They decrease, which makes sense. It should be harder to get a tie the more M&Ms you have. Anything else?
The denominators are powers of 3.
The denominators look like they're powers of 3. Maybe that's just a coincidence because we've only looked at 8. What do you think? Let's multiply by 3 to the 2k minus 1 to clear denominators. Now you get the numbers 1, 5, 33, 245, 1921, 15,525, yada, yada, yada. It turns out all the denominators are powers of 3. Has anybody seen this sequence of numbers before? So I am old enough that I still remember the day in grad school when someone came up to me and said, hey Steve, you got to look at this new site called Google. Do you guys remember a time before Google?
Yeah. AOL chat rooms? Come on, guys.
When you were really young, if there was a word you didn't know, what would you do? Dictionary, right? You would look it up in a dictionary. Maybe the internet's down. Or you might look it up in an encyclopedia. If you want to find out about a subject. It turns out there's an encyclopedia for sequences of integers. It's called the OEIS, the Online Encyclopedia of Integer Sequences. It is a wonderful website. And what you do is you feed it in a string of integers, and it will tell you every single place it knows where that is a sequence. So if you feed in 1, 5, 33, 245, 1921, 1525, go to the website, it tells you it's sequence A084771. The web exists. Use it. There is an enormous amount of information out there. You want to find that information. So it's a little bit hard to see, but it will tell you lots of things. So it's the coefficients of 1 divided by the square root of 1 minus 10x plus 9x squared. It's also the central coefficient of 1 plus 5x plus 4x squared to the n. There may be hope for some kind of nice formulas. It's also the number of paths from 0, 0 to n0 using steps 1, 1, 1, 0, 1, negative 1. Oh, that looks a lot like what we were doing. It's the number of lattice paths. It's the Hankel transform of a certain sequence. Here are some references. Here are some links. Here are some formulas for the generating function. There's a lot of stuff. So what I will do right now, I will go to OEIS. So our sequence was 1, 5, 33, 245, 1921. So if I plug that in, it turns out there's only one sequence that has that as its beginning block, which makes it really nice. If I delete one term, there's now 4 sequences. And so in a situation like this, what it would mean is I should do a little bit more work. But now I have 4 things to try. So the first is the number of cyclic arrangements such that the difference between any 2 neighbors is at least 2. The next number is 2053. Our next number is 1921. Close but different. The next one is 1921. Okay, that's our answer. The next one is 1941, a little bit off. And then the last one is 1889. But it's an incredible website. And it gives you so much information about them. Anybody want to give me a sequence of numbers? 4. 38. Okay, yes?
800.
800. Are you just making these up?
Yeah.
Okay, so we will do 438. Sorry, but the terms do not match anything in the table.
Maybe start at 1.
1. No, because it doesn't have to start with that value. It can be, yes, it can be anywhere in it.
If your sequence is of general interest, please submit it.
Right. If your sequence is interesting. So I actually have submitted some sequences to the website. So if we do 1 438, then it has found 32 examples. It's the sum of n to the n times n plus 1 to the n minus 1 times the exponent. Oh, so it's the OGF. I'm not sure what the OGF is. I know what generating functions is. I'm not sure what, maybe it's the oh my god generating function. There's the number of connected labeled graphs with n nodes. 1 438. Is that what you were thinking of in your head?
Yeah.
Yeah, that's what I thought. Yeah. Oh, you said 800. It's 728.
I must have miscounted.
You must have miscounted. It's yeah, because 468 is too low. Clearly, 556 is too low. Notice over here, it's much further down where you get the 1 438. The next one here is 661, 532, 596, 444, 720. Oh, 727. Oh, maybe you were doing the number of connected labeled 4 colorable graphs on end nodes. So the point is, this is an incredible website. It does not just have the standard sequences that we all know and love. People have spent an enormous amount of time in putting stuff into this. I once gave a talk at Brown when I was a postdoc on how to prove theorems using this website. Is that if you can get a couple of data points and conjecture, you have the formula. How many of you remember proving formulas for the sum of the first n integers or the sum of the first n squares or first n cubes? What method do you use to prove these results? Induction. Induction is a lot easier when you have the induction formula. This is a great way to get that induction formula. If you put in the first few sums, let's put in the first few sums of integers. Let's do the squares. 1 plus 2 squared is? 1 plus 2 squared plus 3 squared? Next one we have to add 30. We could probably add one more, 55. So there's 10 results. The first is the square pyramidal numbers, which is our answer. And the next number would be 91. But it also tells us, and there's a lot of information on this, it also tells us it could be plus the square of the sum of the digits of n. So it goes 91, 140. Our next one was 91, 140, 204, 285, 204, 280. So it'll be interesting to see how long until they disagree. And so of course what we can do now is we can cheat a little bit and just plug in, say, a few more values and not have to do them by hand. And now we're down to just 2 possibilities. If we calculate something like this, it's either the square pyramidal numbers or it is the sequence and first differences include all square numbers exactly once. Okay. So, the point is, incredible way to cull the web if you want to deal with a pattern. So if you try to go to Google, you can put in those numbers and see if somebody has inputted something on that. But this is a great website to search. All right, so just a couple of takeaways. The power of asking the right question. If you ask the right question, that will influence which tools and techniques you use. There's many ways to solve a problem. Different ways will allow you to use different tools. Memoryless techniques, that's one of the most important techniques we've learned this semester, converting the infinite to the finite. There are other ways as well. Experience is an incredibly useful guide. The more things you've seen, the more chance you have of saying, this looks like something I know. How many of you have heard of Richard Feynman? Nobel laureate in physics. He was the one who figured out what was going on as to why the Challenger exploded. He had a reputation for being phenomenal at solving problems. And in one of his books, he talks about how people would come up to him with integrals they couldn't do. And he would look at the integral and immediately solve it. And they'd be amazed at how great he was. And what he said in the book is, well, the people who are coming up to me, they're not idiots. They've probably tried all the standard tools and tricks. I'm not going to waste my time on that. I know most people don't know the trick of differentiating under the integral sign. Let me try that. And not surprisingly, he's looking at a biased set, because they're not going to bring a problem to him that can be solved by the standard techniques. The more things you see, the more chances you have of seeing a connection. Another big theme from today is looking at data the right way. When we looked at the regular plot of the probabilities, it was not clear what the limiting behavior was. But the log-log plot, a straight line. How you present information is extremely important. Now you can be honorable or dishonorable. If you look at a lot of polling companies, the whole points of polls are to influence people's perception. And it's to slant how the data is presented. They do this a lot of times in news stories. My favorite example was, there was a grade strike when I was an undergraduate at Yale. Have I told you the story? And when I went home, they made the national news, and they interviewed 2 random grad students, and they asked them what they felt about the grade strike. And they all came out very strongly in support of the striking graduate students. What they never said is the first person interviewed was the president of the striking organization, and the second person was her vice president. Now, it's possible that the reporter was just walking on campus and just happened to run into them, and I wouldn't be surprised if the president is walking with the vice president at a very stressful time for graduate students, but that information was never conveyed at all in the interview. How you present information is extremely important. The more math you know, the more connections you have. So I think this is a great way to stop. Go grab some ice cream, have a good semester. If you have any questions as you're doing the exams, let me know.